Welcome to the Dam Owner Webinar Education Series by ASDSO. The purpose of these webinars is to help dam owners understand their dams and their responsibilities. We're going to talk about Dam Safety 101. What are the parts of your dams? How do dams function? How can dams fail? And what you can do to prevent failure and to do proper maintenance. Think of a dam as a car. You own one, you know how to use it, you know the basic maintenance, but you know if something isn't quite right with it, and then you know when to take it into a mechanic and let it get checked out. A dam is similar in a lot of ways. It requires maintenance, you need to keep an eye on it to know if something's going wrong, and then you need to know when to call an engineer or a dam safety official to come check it out and make sure everything's operating okay. ASDSO has a series of 2-hour webinars available on their website. These cover a great variety of topics, and I encourage you to check them out. For this video, we're going to be stealing different pieces from some of those webinars. So let's begin by going over the basic parts of a dam. Paul's going to cover the basic parts of an earth embankment dam and a concrete dam.
And when a dam is inspected, sometimes we refer to the left and right. It could be the left wall, training wall of the spillway, the right training wall, the right abutment, the left abutment. And for consistency, whenever you're doing that, the left and right is if you're facing downstream. So if you're on the top of the dam and you're looking downstream, here we would have the right abutment, and then we would have the left abutment of the dam. We have the reservoir, and then we have the top of the dam. In this case, it's an embankment. It's an embankment crest. Now, I'm showing you a dam, and I'm saying it's typical, but there really is no such thing as a typical dam. I like what one of my colleagues says. He says, dams are like snowflakes. There's no two alike. Every one of them is unique. But most dams have typical features, and that's what we're going through right now. So the top of the dam is an embankment crest, and then the upstream slope of the dam, and the downstream slope. And then we have the part where the dam meets the natural terrain. At that intersection, that's called the groin. And you can have the left groin, the left upstream groin, the right upstream groin, the left downstream groin, and the right upstream groin. Then we have a principal spillway. In this case, it's a drop structure type spillway that's out in the reservoir. And there are all different kinds of spillways. But the purpose of the principal spillway is to maintain the reservoir level. So most of the time, water is flowing in the principal spillway. And then we have a conduit that passes through the embankment, and that's the principal spillway conduit. And then a low-level outlet, the discharge point at the toe of the dam. And then we have an outlet channel that conveys the water back into the natural stream. And then we have an auxiliary spillway. Sometimes the principal spillway and auxiliary spillway is combined, and sometimes they're separated. When they're separated, it's generally understood that the auxiliary spillway is there only to pass very rare extreme floods. In most cases, the auxiliary spillway will be activated for the 100-year flood or greater, and that's to prevent the dam from being overtopped. Now, dams are very interesting. They can have a lot of other features like this one does. They can have instrumentation to monitor the conditions within the dam. They can have gates, bridges. You can see in this one there's a bridge over the spillway. There are access roads, conduits and valves, and sometimes there may be a fish ladder at the dam. When you look at a concrete dam, we have a lot of the same nomenclature. A couple things are different. Here we have the left and right abutment like we would have for an earth embankment dam. And then in this case we have the overflow section of the dam. So there's generally a part of the dam that's the spillway, and that's designed to be overflowed. And at the toe of the spillway there's normally a stilling basin to dissipate the energy that goes over that spillway. And then there's the non-overflow section, the part that's designed not to be overtopped. And then the part of the non-overflow section that's above the crest of the spillway is the chimney section. Here's a good example of a big concrete dam under construction, and you can see a cross-section of the dam here, and that in this case is a concrete gravity dam. It's solid concrete, And most concrete dams are built on a rock foundation. They're not built on overburden because they have a very small footprint, often less than a third of what would be the footprint required for an earth embankment dam. And that's, you can have very high flow gradients underneath, and that's why it has to be on a rock foundation.
We've got a few animations here that are going to show the most common ways that earth embankment dams can fail. These include overtopping of the embankment by extreme flood events, which can cause erosion and eventual breach and failure of the dam. Then we have a video on a piping failure, which is when water starts to seep through the dam and start to carry parts of the dam out with it, creating a larger and larger pipe or hole through the dam, eventually causing complete failure. And the third video is on embankment slides. The embankment can become unstable when it becomes saturated, causing a slide and loss of fill material that could cause the entire dam to collapse.
Dams are designed to store runoff resulting from heavy rain. When storage has reached a specific limit, spillways are designed to pass the excess floodwaters, initially through a primary spillway. Many dams are equipped with an emergency spillway to help pass large flood inflows which exceed the capacity of the primary spillway. In an extreme flood, flows can exceed the combined spillway capacity, spill over the top of the dam, and create a very dangerous situation. Overtopping flood flows can rapidly erode down into an earthen embankment dam, leading to an uncontrolled release of the stored waters and causing catastrophic flooding downstream. Most all dams experience seepage to one degree or another. While the dam experiencing seepage may appear in sound condition, there may be damage occurring to the internal structure of the dam. If seepage flow rates appear to be increasing and the flow is not clear and is carrying material, internal erosion or piping is likely occurring. Piping is an erosion process that occurs inside the dam whenever the seepage flow starts eroding embankment materials out of and away from the dam. This starts at the downstream slope or toe and moves rapidly upstream to the impoundment. This process will tend to accelerate as the expanding larger opening or pipe allows for increased seepage flows. If left unattended, the seepage flow and progressive internal erosion will soon get out of control. When the internal pipe or void becomes large enough, the embankment structure above it will collapse. This will result in a failure of the dam's embankment and a potentially catastrophic release of the stored water, which may cause serious property damage and loss of life. One of the most serious dam safety concerns is the stability of the earthen embankment. Unsafe conditions could lead to a major slide that threatens the safety of the dam. A key factor to stability is the location of the phreatic line, or the fully saturated zone of the soils within the embankment. In safe dams, this level is well confined below the surface. Since soils that are fully saturated are not as strong, a higher phreatic line can reduce the ability of the embankment to resist sliding. This is often noted by seepage exiting on the downstream face of the dam. Weak or poorly compacted soils can increase both seepage and the phreatic level, as well as weaken the embankment, contributing to a sliding failure of the dam.
So how do we prevent failures? Well, there's two things: proper design and proper maintenance. The following two videos will show you some of the internal design features that can be very helpful in preventing both slide failures and excess seepage. The following video will talk about overall maintenance activities that should be done to keep your dam in good condition.
Properly designed dams often include an internal drainage system, such as a sand chimney and blanket drain. They serve as a filter to keep seepage from moving any soil, as well as allowing seepage to be removed in a controlled fashion. This lowers the phreatic line and improves the stability of the embankment. For existing dams with a high phreatic line, two alternatives can improve the dam stability. One is to add a drain near the toe to both filter the seepage and lower the phreatic line through a controlled release of the seepage. The second is to add a berm for added resistance and improved stability of the embankment. This does not lower the phreatic line, but improves the dam stability by adding weight to prevent slides in the embankment. Like any infrastructure, dams need to be maintained. Maintenance activities should be performed routinely so that minor problems do not become major. In humid eastern climates, vegetation will grow spontaneously. Unchecked growth of trees, brush, and long grass is undesirable for the following reasons. Trees can become uprooted, damaging the crest or slope of the embankment. Heavy vegetation will make inspection difficult and provide a haven for burrowing animals. Trees and brush can block spillways, reducing the dam's ability to pass large flood flows. Erosion of embankment surfaces is undesirable. Rainfall runoff can create erosion gullies, particularly where the dam meets up with the abutment. Burrowing animals should be controlled. Animal burrows will shorten seepage paths, which increases the potential for piping and internal erosion of embankment material. Sloughing and small surface slides can develop at any time. Surface slides need to be immediately repaired before they increase in size and become a major stability problem. Debris can block the spillway inlet, leading to increased pool levels and possible embankment overtopping. Riprap should be carefully inspected and replaced as needed. Wave action can damage the slope protection, exposing underlying embankment soil to rapid erosion. Debris left to collect on the upstream slope can damage the slope protection and hide problems. Keeping a dam in good condition is important and will prevent problems which could lead to failure.